Section 24.5. Electric potential due to continuous. In this lecture, we will cover several key topics related to electric potential. First, we will discuss how to find the electric field from the electric potential. Then, we will explore equipotential surfaces and their relationship to electric field lines. The main focus will be on calculating the electric potential of continuous charge distributions. We will introduce specific problem-solving strategies for these types of calculations. Finally, we will apply these strategies to several examples, including an electric dipole, a uniformly charged ring, a charged disk, and a finite rod. Let us look at how to find the electric field if the electric potential is known. The electric field components can be found from the potential function using partial derivatives. Specifically, the x component of the electric field is the negative partial derivative of the potential with respect to x. Similarly, the y and z components are the negative partial derivatives with respect to y and z, respectively. In vector notation, this means the electric field is the negative gradient of the potential. This mathematical relationship tells us that the potential changes only in directions where the electric field has a component. For instance, if you move perpendicular to the electric field, the potential remains constant. This brings us to the concept of equipotential surfaces. An equipotential surface is a three-dimensional surface on which the electric potential is the same at every point. A key rule is that equipotential surfaces are always perpendicular to electric field lines at every point. On this slide, we see three examples. For a uniform electric field produced by an infinite sheet of charge, the field lines are parallel, and the equipotential surfaces are parallel planes. For a point charge, the field lines point radially outward, so the equipotential surfaces are concentric spheres centered on the charge. For an electric dipole, the field lines are more complex curves, resulting in equipotential surfaces that are no longer simple spheres or planes, but still intersect the field lines at right angles. To summarize the potential shapes for different charge configurations, an infinite sheet of charge creates a uniform electric field, which corresponds to planar equipotential surfaces. A single point charge creates a spherically symmetric field, resulting in spherically symmetric potential surfaces. An electric dipole creates complex electric field lines, and therefore has non-spherical, more intricate equipotential surfaces. Recognizing these symmetries can help you visualize the physical situation before you begin calculating. Now we consider the electric potential due to continuous charge distributions. To find the potential at a point P, we divide the entire charge distribution into tiny elements, each containing a small amount of charge called dq. We treat each of these infinitesimal elements as a point charge. The small contribution to the potential from one element is Coulomb's constant times dq divided by the distance r to point P. To find the total electric potential at point P, we integrate this expression over the entire charge distribution. The total potential is Coulomb's constant times the integral of dq over r. When solving problems with continuous charge distributions, follow this strategy. First, conceptualize the problem by visualizing the potential and checking for any spatial symmetries. Next, categorize the source as either discrete individual charges or a continuous distribution, which tells you whether to use a sum or an integral. Then, analyze the problem. Remember that electric potential is a scalar quantity, so you can use simple algebraic sums or scalar integrals without worrying about vector components. Finally, finalize your result by checking its consistency and observing how the mathematical expression behaves at extreme distance limits. Note that for finite distributions, we typically define the potential to be 0 at infinity. Let us apply our equations to an electric dipole. A dipole consists of a positive charge q and a negative charge minus q, separated by a distance of 2 a's. First, we calculate the potential at point P on the y-axis. Since P is equidistant from both charges, the positive and negative potential contributions cancel exactly, making the potential at P equal to 0. Next, we evaluate the potential at point R on the positive x-axis. Here, the distance to the positive charge is x plus a, and the distance to the negative charge is x minus a. Summing these scalar contributions gives a total potential of negative 2 times Coulomb's constant times q times a, all divided by x squared minus a squared. Continuing with the dipole, we can analyze the far field approximation. For a point on the x-axis very far from the dipole, the distance x is much greater than the separation distance a. In this limit, the a squared term in the denominator becomes negligible, so the potential approximately equals negative 2 times Coulomb's constant times q times a over x squared. We can also find the x component of the electric field far from the dipole by taking the negative derivative of the potential with respect to x. This gives an electric field approximately equal to negative 4 times Coulomb's constant times q times a over x cubed. Notice the 1 over r cubed falloff of the electric field with distance, which is characteristic of a dipole. Our next example is a uniformly charged ring of radius a and total charge q. We want to find the potential at point P, located on the central axis at a distance x from the center. Because of the ring's symmetry, every charge element dq is the exact same distance from point P, which is the square root of a squared plus x squared. When we integrate dq around the ring, the distance is constant and comes out of the integral. The total potential is simply Coulomb's constant times the total charge q divided by the square root of a squared plus x squared. By taking the negative derivative of this potential with respect to x, we easily find the x component of the electric field along the axis. Now consider a uniformly charged disk of radius r with a surface charge density sigma. We can calculate the potential on the central axis by treating the disk as a set of concentric charged rings. The charge of each thin ring is its surface charge density times its area, which is 2 pi r dr. By substituting this into our previous ring formula and integrating from radius 0 to r, we obtain the total potential. The result is 2 pi times Coulomb's constant times sigma, multiplied by the quantity square root of r squared plus x squared minus x. As before, we can take the negative derivative of this potential expression with respect to x to find the electric field on the axis of the disk. Let us examine a finite line of charge. We have a rod of length L with a uniform linear charge density lambda lying along the x-axis. We want to find the potential at point P, which is a distance a from the origin along the y-axis. We define a tiny segment of length dx with charge dq and integrate along the length of the rod. Evaluating the integral yields the potential as Coulomb's constant times q over L times the natural logarithm of the quantity L plus the square root of a squared plus L squared, all divided by a. If the length of the rod is much smaller than the distance a, this expression simplifies to the potential of a point charge, which is Coulomb's constant times q over a. To summarize the key points of this section, the electric field is the negative gradient of the electric potential, meaning you can find the field by taking spatial derivatives of the potential. Equipotential surfaces are always perpendicular to electric field lines everywhere in space. The potential due to a continuous charge distribution is calculated by integrating Coulomb's constant times the charge element dq over the distance r. Finally, for highly symmetrical distributions like rings or disks, it is often much easier to calculate the electric potential first and then differentiate it to find the electric field, because potential is a scalar quantity. Let us end with 2 review questions to test your understanding. First, if the electric potential is constant throughout a certain region of space, What can you conclude about the electric field in that region? Second, why is it generally easier to calculate the electric field by first finding the potential and then differentiating, rather than integrating the vector field directly? Take some time to think about these conceptual questions.